Liga a câmera. Hello everyone, welcome to today's seminar. Today we have Vincenzo Mainieri, who has a PhD in physics from the University of Rome, Tre, in Italy. And he's currently a full astronomer at the European Southern Observatory in Garching, where he was also a student and a fellow. He's the current project scientist for Foremost and the upcoming Mosaic at ELT and the potential WST MOS facilities at ESO. His research is focused on AGN, and he has been using JWST, Symphony, and IRIS. So thank you, Vincenzo, for accepting our invitation. The floor is yours when you're ready.
Okay, thanks a lot, Anna. Thanks everyone for inviting me. Yes, so it's a great pleasure today. I want to tell you about WST, where WST stands for the Wide Field Spectroscopic Telescope. And WST at this stage is a concept study. So we are thinking about the potential new facility. And as Anna said, this is in the context of this potentially being the next ESO facility after the ELT. The study is funded at the moment for a grant from the European Union. And what I show you today is, of course, the output of the work of many people in the WST team, but also from a very broad scientific community. Okay, so let me start saying that the necessity, I mean, the need from the scientific community of a facility dedicated to spectroscopic survey on a telescope of the size of 8 meters has been and is currently still, let's say, a priority that appear in many strategic plans for astronomy across the globe, from the US to Canada, but also in Asia and in Europe. Because this started in Europe, I just wanted to mention that what we have is an entity named Astronet that essentially forecasts the needs for astronomy in the at least ground-based, but also space-based in the future. And the last Astronet report that was issued a few years ago, a ground-based facility with this key characteristic to have a very wide field of view, but also high multiplexing, was identified as a priority. And this is also strictly linked, if you want, with synergies with other major facilities, either from the ground, like Vera Rubin, that is starting now, but also from space, both JWST, but also thinking really satellites covering very wide area on the sky, like Euclid in the future of Roman. So what WST is trying to answer to this necessity from the community. And in a sentence, I would say it's an innovative facility, cannot be otherwise. Otherwise, there is no, will not make sense to invest so much effort and so much money on a new facility, which we think really will tackle what we consider at this stage really open scientific questions. But open scientific question, not thinking to the next few years, but really to 2040 plus, because to build such a facility will require more than a decade. So we really have to think about the science you want to do or you think will be important in the 2040s. And what we believe is that WST, such a facility, can really cover a very broad range of scientific topics. And this nice image put together by Maria Cristina from our communication team is really trying to exemplify visually the range of physical scale, for example, that this facility will tackle. So you really go from few hundred kilometers where you really want to study details, for example, object in our solar system, down to then up to parsec scales when you start to zoom out and see, for example, conglomerate of stars, out to kiloparsec scale when you want to characterize the structure, the kinematics, for example, of nearby galaxies, and then zooming out farther and farther really to see the environment in which this galaxy lives, potentially also transient and extreme objects like GRB or black holes, and really then zooming out to the larger scale where you want to really reconstruct the distribution of matter on 100 megaparsec scale, the so-called cosmic web. So this is the message. I mean, really, WST is not conceived as an experiment to tackle one single specific scientific question, but really want to cover a broad range of scientific topics, so serve a very broad scientific community. So from the organizational side, WST got together as a consortium of institutes. So currently we have 25 institutes that you can see in the map are spread mostly in Europe because this is where it started, but also we have several universities involved in Australia. And this is essentially the consortium that applied for this funding into the EU that we are currently using to do this concept study. But apart from, let's say, this entity that is well structured, the consortium, WST is an open project to the community from the scientific perspective. In fact, we have a very broad science team of more than 800 people at the moment that are really spread across the globe. And of course, there are many also colleagues in Brazil. So it's really open, and this is actually a very important message that I would like to pass today. Let me give you a bit of numbers just to fix in your mind what is WST in terms of capabilities. So we are talking about a new facility, a brand new facility, so a new telescope, which an aperture of 12 meter, which essentially, if you compare to the VLT, will means that the collecting area that we have is double that of one UT at the ELT. And the key facility, the key characteristic, as you can see in the table, is the very wide field of view. It will cover in one observation 3 square degrees of the sky. And the telescope, as it conceived, can efficiently work from the blue end of the optical up to the H band. And then the concept of this facility involved three modes, three set of instruments, if you want. These are color-coded in green, yellow, and red. So in green is essentially a multi-object spectrograph at low resolution, which means a spectral resolution of 3000, 4000. Here, really, the key characteristic is the multiplexing, how many objects you can observe at once. And we are talking about 30,000 objects you can observe at once in this large field of view, and covers the optical. And then there is a mode for high spectral resolution, mostly triggered by galactic science, as I will tell you in a minute, but also IGM studies. And this is a smaller multiplexing. This is associated also to the surface density of targets suitable for this mode. But the spectral resolution here is the key parameter, which go up to 40,000 spectral resolution, and will be able to observe in specific windows in the optical, 4 windows in the optical. And then the third mode we have conceived in WST is an integral field spectrograph, so a monolithic IFU of 3 by 3 square arc minute. So if you are familiar, for example, with MUSE at VLT, which is a very successful instrument we have here, it's an integral field spectrograph, monolithic, so one field, continuous field. This is essentially 9 times the area of MUSE. And we'll cover fully the optical bands from 370 to 970 nanometer. And the other thing that is important that you can do all this at the same time. So you can observe with the multi-object spectrograph, with the integral field spectrograph at the same time. And finally, the last characteristic I want to mention is that we have implemented since the beginning of the concept the possibility to do target of opportunity observation. And I will get back to this towards the end of the talk. Okay, so this was a table, but just to graphically show you, I think it's also more impactful. You have in orange the field of view of these 3 square degrees I just described, and you can compare on the left with the field of view of the VLT. As you can see, we're talking about a huge increase in field of view of what we will have with ELT, which is even smaller. These are totally complementary, let's say, to the current facility we have at TESO. Then you can see in the center, there's a little blue hole, as this is essentially where the IFS will be located. And if you zoom in this hole in the center, you can see on the right-hand side, the IFS is that red square there, and you can compare with MUSE, that is the orange-like square on the top right. And you can see, of course, the increasing field of view of 9 times compared to MUSE. And another thing I want to mention is that the IFS can move in this larger bluish area. So you can observe with the MOS on one field, and at the same time, you can move the IFS around. And just to give you also a graphical representation of how can work this parallel observation between MOSS and IFS, assume you have your 30,000 fibers, you are located on the object on sky. These are the white circle on the left. And then on the center, as I said, you have your IFS. And this is for one exposure, for example. The second one, you can reconfigure the fiber, looking at other 30,000 objects in the same field of view, but then the IFS can move. And so you can essentially get, without moving the telescope, a very, say, large area covered with the IFS at the same time. Okay. When you think about a facility that, as I said, will start for the 2040, but is such a large investment economically also that you have to think about even farther in the future. So we already have in a concept study thought about what could be a potential upgrade for such a facility. So the most obvious one is to extend the wavelength coverage. So at the moment, as I said, the MOSS is optical, but of course an obvious upgrade would be to extend this in the near infrared up to the H band at least. Another possibility that could be useful for some science cases is to have mini bundles of fibers, so you have small IFU that you can locate in different positions in the field of view. And another, what was an upgrade plan, but actually now is in our baseline concept, is to correct for the turbulence of the atmosphere, but only what we call the ground layer. So the first, say, kilometer or so of the atmosphere, and there you really can gain a lot in terms of image quality. And just to give you some numbers on the left, you have in purple the full width of maximum. So let's say the image quality that you will have in the integral field spectrograph without any correction. So without AO correction, and in greenish, you see the huge improvement in image quality when you correct for the turbulence of the atmosphere and the ground layer. So this is very good news, especially if you are interested in of course, image quality means also concentrating more the light, so potentially going fainter, but also means resolving smaller and smaller physical scale. Now, WST, as I said, is ambitious, but is also transformational in the sense that really stand up compared to what we currently have or currently plan. One way to see it, for example, on the left plot, you have for the multi-object spectrograph, the multiplexing of this facility as a function of aperture of the telescope in which they are. And I put in this plot most of the multi-object spectrograph we have, or even they're in planning or in construction, and WST really stand out, both in terms of multiplexing especially, but also compared to other without multiplexing also in collecting area. And on the right plot instead is for the integral field spectrograph, and here it's even more dramatic. You want to jump in capabilities compared to what we have. You can see that the field of view of the IFS is way above 1 order of magnitude, almost above what we currently have or we will have in a few years. So this is, of course, not the whole story. Of course, then we see how this propagates on the scientific output, but of course, you are opening a new parameter space. Okay, a few more slides more on the technical side, and then I will dive into the science. So this is just to show you the current concept of the facility. So as I said, we have a telescope of 8 or 12 meter aperture. You can see here in the middle, which has is a challenge in itself, because you want at the same time to collect lights to feed this multi-object spectrograph, but also have the possibility to feed an integral field spectrograph. The primary mirror is 12 meters, so you cannot do in one single piece of glass, so you need to segment it like it is essentially at Keck, but also at the ELT. And in fact, what we will plan to use for WST will be to reuse the same segments, mirror segments that have been developed for the ELT. So there has been a huge amount of study put into that, and that will serve perfectly also WST. Once you collect the lights with the mirror, the different optics, then you feed essentially two sets of instruments, as I mentioned, the multi-object spectrograph, and this is, I don't know if you can see my cursor, but it's this box close to the telescope here, so those 30,000 fibers. But then the light will go down, as you can see in the top right, to what we call the IFS station. And this is a huge amount of spectrograph, because you can imagine you want to get spectra for each single pixel in a 3 by 3 square arc minute field of view. And these at the moment are more than 140 spectrograph. So actually this require a huge volume, and so this means that the telescope should be at a certain altitude from the ground, which is also a good thing because you have less turbulence. So as I mentioned, in itself, the telescope is not something that has been done necessarily in the past. So there's been also effort in designing it. The main challenge was to be able to feed lights both to the MOS and the IFS, as I said. But also, if you compare in terms of NTNU, meaning the product between the area, the collecting area, and the angle on sky that you can observe, so the field of view, this is stand above essentially all telescopes that have been built on the ground in the optical. Just to give you also a flavor about how innovative you need to be when you start increasing so much basic numbers like multiplexing, one key things in order to be able to position 30,000 fibers, because we're talking about fibers to collect lights from 30,000 objects on sky, you need to develop new technology for this fiber positioner. This is an area which we are investing a lot of effort, and here just to show you potentially different concept we are studying, and but just as a proof of concept that we can do it, in the middle you have one realization for one of this positioner which allow us already to reach close to 27,000 fibers on this 3 square arc minute area, so it can be done. Of course, also the spectrograph need to be quite efficient, but also you need to take into account that you need hundreds of them. And also in this area, the engineers who work with us need to put quite some effort in defining the best optical path, but also there is a lot of technology development on the detectors. Now there is the possibility to use CMOS detector rather than CCD. And here, what people are really looking to in great detail is the ability to curve such detector. If you're able to curve the detector, then you have smaller optics, which means less cost, less loss in terms of throughput, and so on and so forth. So there is a lot of development also on the technological side. Now, on the next question would be, where would you think WST should be? I mean, the obvious answer is close to a site where ESO has a facility. And I mean, for obvious reason, you don't want to build something from scratch. You want a good site, but you want to take advantage also of facilities that are already in place. And on the right, you can see a map of the desert in the north of Chile, where Paranal is. You have the BLT on the bottom left, then there is the ELT close by. This is where the current facility of ESO are. And the different dots with the name, La Montura, La Chira, Ventarones, and McKenna are 4 sites which potentially could host WST. They have the advantage that at least 2 of them are inside what is essentially where ESO is able to build things, because there is an agreement with Chile, but the other also are not far away. And so they are close enough to use the same facilities, lodging, but also engineering facilities. And at the same time, they are not exactly where VLT or ELT are, because one thing you need to worry about when you do a spectrograph in the optical is that you don't want a contamination from the laser that both VLT and in the future ELT will largely use. So it's close, but not close, not too close. So what we are doing is to monitor these sites. I mean, at least for this one in yellow, La Chira, we have already a lot of historical data on the atmospheric conditions there, and we are currently collecting more data to see if it's a suitable site for a facility like WST. This is for the site, but also, I mean, we need to be very conscious of how we're going to power such a facility. There is going to be a huge need of energy, especially for cooling the facility. And that's already in place, a very green, let's say, source of energy in Paranal, which is this large solar plant that is serving already VLT and will serve ELT, and expanding just a bit, this will be more than enough to serve also WST. So there is definitely a very good synergy there. Okay. Let me get to the science. So, of course, as I told you at the beginning, WST want to cover a very broad range of science topics. And here, I just want to mention the big areas, and then I will dive a bit more in details in some of them. So we start really from the very early universe, starting to understand how reionization happened, which is also connected how the first stars and first galaxy formed. But this is also linked to the different cosmological model we have. So being able to differentiate between different inflationary model down to fundamental physics, like understanding which is the sum of the mass of all neutrinos. And then when we zoom a bit in and we start resolving galaxy, here also thanks to the IFS, is really trying to understand how galaxy assemble their mass over time, over cosmic time, but also how which are the physical process that govern this assembly of mass, taking into account the environment in which these galaxies live. And this is also linked, if you want, to the growth of black holes at the center of these galaxies, and where we want to cover a very broad range of masses, but also cosmic time. And that, of course, is also linked to variability of the black hole accretion, but also in general to, if you want, a more dynamical universe where you have transients. And here there is, as I said, strong synergies with Vera Rubin, for example, between the others. And this is also then even go outside the electromagnetic spectrum when you think about the transient events that can generate gravitational waves. And then also looking closer to us in our own Milky Way on the local group, understanding the evolution of stars, especially the production of heavy elements, and also related to the planet formation characterization of the host properties of the galaxy. Of the planets. So how do we cover such a broad range of science? And this is also thanks to the engagement of the scientific community in general. As I mentioned at the beginning, WST is a totally open collaboration in terms of scientific involvement. And at the moment, we have a science team with more than 800 scientists. And we have organized the science team in 5 different working groups. You can see here they cover the classical area from time domain to galactic studies to resolve stellar population, extragalactic science and cosmology. And there are different coordinators, mostly early career or junior faculty members. So this is very promising, of course, because we're thinking about a facility that will come in 15 years at least. But we also have a working group that go across this. So for example, recently we formed one that is focusing on agent physics, black hole accretion. And finally, also, I want to mention that, of course, we organize meetings, but also we participate in more general meetings. So just to mention, this is mostly focused on Europe. There's going to be a European Astronomical Society meeting in Lausanne in July. We will be there with a special session on WST, but also ESO. I will tell you more about this initiative named Expanding Horizon to identify the new ESO facilities, organizing a workshop in July here at ESO to discuss with the community. And of course, we will bring there also our scientific ideas. Now, let me dive through some of the science that we think is driving the design of WST, why we need WST essentially. So let me start from cosmology. In here, really, the new parameter space that WST is opening is to do precise cosmology at higher redshift, which higher redshift in this context means above redshift 2.5. And I think this is possible mostly because with WST, we can really use different tracers of the cosmological environment as a function of redshift. And this is clarified, shown in this colorful diagram on the left, which essentially you have different colors for different tracers. And really, you can go from cosmology in the local universe up to the reionization epoch using different tracers. And this convert into the ability really to do sub-percentage measurements. And this is, just to give you an example, the 2 plots on the bottom here, you have the forecast of what you can do in precision when measuring, for example, BAO parameters like on the left of the growth of structure on the right. And if you look at the different curves, if you focus your attention on the red one, the red one is what you can do with WST above redshift of 2. You can compare to whatever else can be done, either now, for example, DESI in blue, or future facility like MUST, which is another spectroscopic facility that currently China is developing. Essentially, what WST is doing is new above redshift 3, 3.5. So it's really opening cosmology at high redshift, which can be very important to constrain new cosmological models, but also can have a series of consequences because it can put very strong constraint on multiple things. And in particular, going back to fundamental physics, I want to mention two. So we know that neutrinos have masses. I mean, they are not zero masses. There is flavor oscillation in the neutrinos that from our sun get through the atmosphere. That's been proven in accelerators that neutrinos have no zero masses, but characterizing which is the sum of all the neutrino flavors, it's still open. In the plot on the bottom or left, you see the sign contours, and this is the current constraint from Planck on the neutrino masses. And you can see they're very, very loose. So the message here that I want to pass is that even in the most conservative scenario in which the neutrino mass is very low, in this particular case, 0.06 electron volt, WST, and these are the contours in black, can really give you high confidence on the evidence that the neutrino have a mass and determine it. But also, if you think about different cosmological models, different inflationary models, you can see on the right the power of having the precision on these measurements that you can do with WST. What you see there is the so-called FNL that essentially can distinguish between different inflationary models. And a bit as a function of time, you have the measurements on this parameter. You can do, we have been able to do with Planck, DESI, and with other experiments in the near future. The point here is that the uncertainty is usually large enough that you cannot really distinguish, for example, between these two inflationary models, but only when you are able to shrink to 3D percentage precision on the measurements that you can do with WST, you can distinguish, for example, between a single field or a multi-field inflationary model. So I think this is really transformational in cosmology. But also thinking about cosmology, of course, the massive structure in our universe, like galaxy cluster, have been used as a laboratory for cosmological measurements. And here, WST still can do new science, because here you really can do a comprehensive overview of the massive structure in our universe, and really linking their properties, their scale, the masses with the large-scale structures surrounding them. And here again, it's really a strong synergy both with X-ray satellites, missions, current one or future, because with those you can trace the hot ISM, IGM, but also here there is a strong synergy between the different modes we have in WST. You can imagine with the integral field spectrograph, you can really characterize the center of the clusters, the different kinematics of the cluster members. But then with the MOS, you can cover a much larger area, so you can connect the massive structure with the large-scale structure surrounding him. And then moving to the reionization epoch here, I wanted to highlight a science case that I love because there is a strong synergies with SKA. So SKA in its current foreseen capabilities will allow us to trace neutral gas on very large patch of the sky at very high redshift up to reionization. And this is, for example, thanks to using the 21 centimeter lines. And you can see in this plot I put on the right simulation in blue, essentially you have the brightness, temperature, so essentially a map, if you want, of the natural gas at the reionization epoch. And look at the scale, we're talking about hundreds of megaparsec scale. Now a key thing here will be to validate this, but also to essentially characterize the galaxies that live in these empty spaces where the gas has been already reionized. And this is where the synergies with WST, with a spectroscopic facility WST, come in, because then you do not only get the redshift of the sources in this large patch of the sky, but also you can characterize the physical properties of these sources. For example, if you want to distinguish between a scenario in which reionization is driven by few very star-bursting galaxies that are able to inject in the medium a large quantity of UV photons, from a scenario in which rather you have a much larger population of galaxies, but with lower star formation rate that are contributing to ionization. That's something you can essentially distinguish with the synergy with the spectroscopic survey like WST can do. Really, you can characterize the source of the ionization, as well as validating the size of the ionized bubbles that you had detected in 21 centimeter. Another area in which WST will be really transformational is the large-scale structure, also the tracing how gas is distributed in the IgM, in the ISM, and the CGM. Here, really, there is a jump on what you can do with integral field spectrograph now and what you can do with WST. With WST, you can trace essentially filaments on tens of megaparsecs. So really representative patch of the sky. You can have you can see a simulation there on the top right, and you can characterize the filaments, the gas density in these filaments, and you can trace the morphology, the topology of these filaments that form the cosmic web. But not only this, then for single galaxy inside these filaments, you can trace the circumgalactic medium in emission. One of, I think, more remarkable result from MUSE, for example, but also from KCWI at Keck, has been the detection, the ability to see circumgalactic medium in emission from Lyman alpha, for example. And this is great because then you can characterize the properties of the CGM, its kinematics, and potentially with other lines also the metallicity. And this is directly linked to understanding how the flow of gas go from ISM scale to CGM to intergalactic medium scale. And so you can do that also with WST on many, many galaxies inside these filaments. And finally, in the bottom plot is to show you we are able to trace the filaments in emission in the center, but then you can even do more on larger scale, because then you can use tomography in absorption with the MOS to trace the distribution really of matter on very large scale, so that you can connect really these filaments with the halo. So we are really going from multiple scale, and this is, I think, the only way you can really trace the baryon cycle if you want in all this complexity. Now, zooming in closer to us, when we think about galactic science, of course, that we want to do in the 2040, we need to think in an era in which we have already completed Gaia since some time. We have the final release of Gaia, but also we had the spectroscopic follow-up. Foremost, for example, is a facility that we have here at ESO that we are currently commissioning, and soon we start, and we do a large spectroscopic survey on the Milky Way, but also moons is equivalent in the near infrared, but WAVE, other spectrograph. So what is left to be done in the 2040s on galactic science? Well, our working group thinks that there are three broad themes where still there will be very important open questions. And the broad themes are understanding the origin of elements, understanding how the Milky Way form, but also related to the formation and the origin of planets and stars. And let me give you a few examples of that. So origin of elements is a very important one. I mean, how heavy elements are formed through neutron capture process, which of these processes are the more relevant one, which potentially are not known yet. And here essentially is the driver to have high spectral resolution. As I mentioned at the beginning, for WST, we foreseen to have a mode that provides spectra with a spectral resolution of 40,000. And the plot here on the bottom, done by Georgios Korkapatis, is essentially to show you the importance, I mean, but to show graphically the importance of having high spectral resolution when you want to essentially characterize with precision the chemical abundances. And here in the plot you have, as a function of wavelength, some cherry-picked elements. And the box there is just for you to compare the red box, the elements that will be accessible on that wavelength, for example, for 20,000 on the left, and what you have with 40,000 on the right. So here is not only sensitivity, not only the fact that you go deeper, but also the fact that you are able to blend lines, which means that you have a much more precise information on the chemical composition of that star. Having a detailed abundances, it's very important also when you want to reconstruct the history, the formation history of the Milky Way. And of course, this is something that also current and upcoming spectroscopic facility will do. But here with WST, you can cover, for example, the whole Milky Way. And again, just to graphically show you the difference between what we will be able to do with foremost soon. These are essentially the dashed lines in green and red. This is essentially the volume that can be covered by in high resolution by foremost for different kind of stars. And the same lines, but the continuing one, show you the increase of volume where you can do with WST. The main message, especially when you go to red clump stars, is that you can cover essentially all the Milky Way and the nearby galaxies, including satellites from the Milky Way, like the Magellan Clouds. And this is very important because different regions have different population and structures. So you want to see how the chemical enrichment is distributed in this different part of our own galaxy. And that's the only way which you can reconstruct the history of the formation of the Milky Way. When it comes to planets, here, just to be clear, we are not thinking about characterizing the planet's properties, but rather the important synergy that we see is to characterize the host star. And here the synergy is with many facilities that either are already in place or will be launched, like Plato soon or Roman in the future. And here really we expect a huge amount of planets detected from this new facility. Here the point is to characterize the host star. And I want to just that you focus your attention on the red histogram on the bottom. That's the distribution of the predicted magnitude for the stars hosting planets detected by Roman. And you can see you go down to 20 magnitude in G-band, which means you need something like WST to be able to get high resolution spectroscopy for this faint magnitude. But there is also a specific case in which you studying the chemical properties of the host star. You can also put constraint on the properties of the planets. And this is a specific, maybe a niche area, but very interesting one in which you can study in detail what are called metal-polluted white dwarfs. Yes, the idea these white dwarfs are polluted. The metals are coming from planets that essentially have collapsed on their host stars. And that brings me to general time domain. And here, the message I want to pass is that really there is a very new but also exciting science that you can do on multiple scales. I mentioned already supermassive black holes several times, but here really is to characterize the mass distribution of the black holes, but also the environment in which they live on a very broad range of cosmic time. And of course, here the synergy is also to characterize dual black hole and characterize how frequent emerging of supermassive black hole, but also stellar mass black hole can happen is directly linked with gravitational wave productions. All possible transients you can think of, from flares on stellar size object, but also an explosion of supernova, GRB, and tidal disruption. Stellar variability is an area in which we learn a lot from Gaia. We will have even more from LSST. But also transient or variable object like in our own solar system, characterization of extrasolar planets also. That will be an area in which the integral field spectrograph of WST will be very important. And the plot here is just to show you a bit the range in terms of time scales and absolute magnitude of variable events as we know now. So keep in mind that could be new things will come, for example, from LSST. But what I want to tell you is that what we had built in WST since the very beginning is a time domain capabilities. What I mean with that is that we foreseen we will be able to associate a certain fraction of the fibers we have to target of opportunity. So in any pointing we will do with WST, we will be able to have a fraction of the fibers to allocate to target of opportunity that have been triggered by another facility in the last very recent past. But also another area which we are opening in science, in my opinion, is the fact that we will observe the same object multiple times, and this will allow you to detect spectral variability, spectroscopic variability, and this is a way you can potentially detect new transient and new physics. And then one important science case also for WST is the synergy with the next generation of gravitational wave detectors. So what is revolutionary here, when we will have the new generation of gravitational wave detectors, which could happen in the same time scale of WST, so 2040, there are at least two concepts. One is named the Einstein telescope in Europe, but also there is the Cosmic Explorer in the US. But in the histogram on the bottom, you see the predicted essentially binary neutron stars mergers that this new facility will be able to detect as a function of redshift. Now, if you focus only on the brown and purple histograms, these are essentially the events for which they will have an uncertainty on the location of sky of the order up to 10 square degree. And so this immediately tell you that we are talking about thousands of such events with uncertainty on sky of, as I said, up to 10 square degree. So you understand that you need a wide field facility like WST to follow up the potential electromagnetic counterpart of this gravitational wave event. And so you can use the IFS on the high probability location, but then you can use the MOS also to track many, many more targets in this error box. Okay, let me now switch to the challenges. There are many, of course, I told you already technologically, but also how you want to run multiple survey in parallel using 3 different observing modes, the ability to put in a target of opportunity, but also manage a huge quantity of data, being able to process this data quickly enough if you want to trigger alert, for example, from spectroscopic variability. So there are multiple challenges, but I want to give you an idea of how you can run in parallel, for example, different surveys. So you can have, for example, 2 different scenarios. One is in which your survey is driven by the integral field spectroscope. Sorry. So the telescope points to a specific region where you have an object you want to observe with the integral field spectrum, for example, a massive cluster of galaxies. And here you go deep, you can do potentially a mosaic to cover the whole cluster of galaxies. But then in the field of view of this 3 square degree, you can put multiple fibers for many other objects that are related to this massive structure. So along the filaments that feeds, for example, this massive structure. And then you can use the spare fiber to target other objects in the field of view, which are potentially not related to the science goal, but to other survey, for example, cosmology survey that is covering essentially all sky. And then finally, as I told you, there is a fraction of fibers that are for target of opportunity. And then you can have the opposite. You just are driven by the MOS. So you want to sample a very large patch of sky with 3 square degree. So you define your fibers, you put them there. Again, some of them will go for other science cases and some for target of opportunity. But if you zoom in, you have this hole in the center, as I told you. And this is an area where you start essentially, you start observing with the integral field spectrograph. And you have the ability for free while you're doing your MOS survey to get very deep IFS exposure, like blank field. And these are very, very powerful, as we observed with MUSE. So that brings me to the discovery power. I mean, of course, you want also to try to quantify how much discovery power, apart from the things you know, discovery power of things you don't know, so the unknown unknowns. And this is very difficult, of course. And I mean, this is, of course, always the case. You define a facility, an instrument, and you build it based on science cases, but maybe you don't predict some that will become mainstream when the instrument or the facility is up and running. Just to give you 2 examples, when the science case for the VLT was built, there was no mention whatsoever of extrasolar planet, and then became actually a driving science case for some instrumentation of VLT. Also, when MUSE was built, there was no mention whatsoever of the ability to trace the circumgalactic medium in emission, as I mentioned, and this became one of the key results of MUSE. So you cannot predict it. But I mean, just let me give you 2 considerations. On the powers of numbers, we are going to have MOS with 30,000. You're going to do large scale sky survey. And so you're talking about hundreds of millions of objects and hundreds and thousands and not tens of millions of stars. And so if you just think about Sloan, and that's the distribution, for example, of age versus stellar mass, you can have with the full power of the Sloan capabilities. If you start dissecting either on redshift or on different properties, you can see how you lose the parameter space. So this is just to mention the ability that you may have to have new discovery power just thanks to the numbers that you are going to assemble. But also the integral field spectrograph has another characteristic. You don't do any preselection. As I mentioned, you get, for example, for free patch of the sky, very deep, which we haven't done, no preselection. You will get a spectra essentially for everything there. And this has been also a huge burst of the scientific productivity of Muse. The number of papers, of referee papers as a function of time for Muse is essentially another slope compared to any other instrument at ESO. This is due to the fact that it's very efficient, but it's also due to the fact that you don't do any preselection, so you came up with new discoveries. And of course, just worth mentioning the fact that, in my opinion, we are also opening new science with this time domain machine that we are building, the ability to detect variability on the spectral side. How can we, I hope I convince you that this is an interesting project, but how can actually happen? And here I think it's very important that ESO started planning for the future. So I hope you have heard of this Expanding Horizon initiative that ESO launched 1 year and a half ago. And this is an initiative towards the community, towards essentially, yes, the community, but actually it's open to the whole scientific community worldwide, to define which is the next ESO large facility after ELT. And as I say, this is a facility that will be up and running not before 2040. And of course, we are working because this can be WST. This is the framework in which we think WST can happen. And just want to show you a bit of an historical perspective of ESO has developed its own facilities over time. If you look at the aperture of the telescope, this has been steadily increasing from the 3.6 meter Basilia, then we have ELT now at 8 meter, and then ELT soon, this is 39 meters. If you look at the resolution, again, we get to finer and finer physical scale down to millisecond with the ELT. But on field of view, we follow a different trend. We essentially are either stationary or we go down. And similar for multiplexing, there is no increase. So really, having WST as the future facility will reverse this trend if you want. On one side, you will go back to VLT kind of aperture and resolution, but what you really burst is the multiplexing of the field of view. So if you want, this is a way to create a new parameter space at ESO. And this is my final slide. I just want to mention a bit what is in front of us, what has happened and what is happening, because we really like to invite you to participate, of course, if you find this interesting. So in terms of science, we published back in 2024 our first white paper to essentially share with the community the scientific ideas that were driving the idea to have WST. In the meantime, ESO has called the community for white papers. There was a call for ESO white papers to be submitted in December, and I'm aware of more than 70 that actually are requesting a facility like WST. What is coming next? There is this workshop at ESO in July that I mentioned, and here, of course, will be a useful, say, occasion to discuss the science of what we want to do with the next facility, so we will be there. But also as WST science team, we are preparing a series of white papers to be published next year. So this is a very exciting time from the science perspective also, because we really want to refine and make it as transformational as possible, the science driver for WST, why we want to have WST. So, and this is led by the science team that I just described, in which everyone is welcome. So I would really like to invite you to consider be part of it if you're not yet. And with that, I want to conclude. And this is also a link to our webpage where you can essentially register for the science team, or you can just drop me an email if you want. And I also want to advertise, we have a bi-month, every other month newsletter names the WST Chronicle that is publicly available on our website, and also you can find more information. And I will stop here.
Thank you, Vincenzo. Do we have questions? Or are we all like, wow?
Hi, Vincenzo. Thaisa.
Hi, Thaisa.
I was impressed about this possibility to use two instruments to observe the same field, right? So, yes. So in the case, for example, that you showed the IFS and multi-object spectroscopy, then the field exactly that you are going to observe with IFS is in the middle, but it's not exactly the same field that the fibers will be positioned. Yeah. It's not exactly the same field. It's inside it. It's inside it. Yeah.
Yes. You have this little hole in the center of few arcminute 9 by 9. So if you want, that doesn't impact anything on the large scale. So for example, if you want to do a cosmology survey or cosmic web, having this hole will not introduce, if you want, any bias possible because it's a very small one. But at the same time, you can, for the IFS, this is a very large area. I mean, in the sense we are talking about square arcminute, so which for an IFS is huge. So for me, that is a very add-on in the sense, one thing that for me would be important would be that you do your MOS survey and always you have the IFS operating, and for free, if you want, you will get very, very deep blank, deep fields. We had to spend 100 hours to get one blank field with Muse, which had created I don't know many scientific results. With WST, you can do that in a few days. So it's very, I think, very important that. Yes, I mean, of course, the challenge is also not the challenge. I mean, the challenge could be to find enough targets for the MOS where you're pointing for the IFS sometimes, but the match between the multiplexing and the collecting area is such that we believe we can have enough targets for the 30,000 fibers, because you can go very deep, essentially, to 25th magnitude at least.
Yeah, very interesting. Very, very unique. Thank you.
You're welcome.
Yeah, I was going to ask a question about how challenging it will be to allocate the fibers. For instance, now we're seeing with the prime focus spectrograph that we are part of, and it's very, very challenging to schedule the observations. And if it's in survey mode, it's easier. But if it's a case by cases basis, a semester, I don't know how it's going to be. So my first question is it going to be like a survey telescope only, or you apply for time for different?
Yeah, no, it's conceived as a survey telescope. I mean, it must be as a survey telescope, but that doesn't imply that you essentially is not an experiment, just to be sure. You were not going to target one specific science case and one specific survey. And this is also due to the fact, as you mentioned, that you want to have a variety of science cases. Otherwise, you will not be able to easily configure the fibers. In the sense, you will not have potentially enough targets or to different conditions. So it's going to be a survey. I mean, how it's going to be, we decide ISO, if ever ISO will approve. But I mean, the way we conceive it is that this is a survey telescope, so we run a survey. Yes, challenging of positioning the fibers is also related a bit on more technological aspects. I mean, for foremost, but also for other, there is a limitation on the way you can position fibers according where the other fiber is. So you have conflicts and stuff like that. New position that the engineers are developing should minimize that. So that could help in that regards. The other thing, yeah, I mean, that's for the challenges. I'm not sure if you have specifically something in mind with PFS that is, you say in visitor mode, because of the lack of targets, or because of what are the challenges?
There's the survey, and there's also that you can apply for time.
Okay.
And
yeah, I understand.
Challenging to organize things, and
okay.
We were
no,
trying.
I would imagine that WST will be a survey facility. And then, of course, you can imagine you can ingest, you can have an underlying main set of survey ongoing, and then you can ingest additional targets. Of course, target of opportunity, we say, but I mean, there is going to be potentially the possibility to include, if new scientific needs appear, to include new targets, I believe.
Do you have more questions? If not, I have a final one. You mentioned like synergies with LSST and so on, but in principle, LSST will have finished.
Yes.
So what do you mean by the synergies that?
Yes, yes, absolutely. No, that's an excellent question, a very relevant one. Okay, LSST, different level of answer. The first one is transients can be done also not live, in the sense you can think about characterization of the properties of the object where the transient has happened. So there is a long term, but of course we cannot imagine something at WST without the equivalent in the imaging. So we do believe that having something like WST could be, let's say, an obvious reason why you want to keep Rubin up and running much longer than what it is now. And in fact, there has been, let's say, at meetings, this kind of arguments. Of course, funding-wise, this is totally to be seen. But also we are developing the possibility to have with WST companion, let's say, facility dedicated to imaging. Nothing comparable to LSST in terms of size, but still it can provide you imaging on large patch of the sky, which can trigger, if you want, also follow-up, spectroscopic follow-up. So the answer is a bit, let's say, motivationally. I think something at WST will motivate the community to have an imaging capabilities that match. And yeah, but yes.
But yeah, but LSST, I mean, there are plans.
Yeah, potentially LSST, of course, but yeah, has to be seen.
Very exciting. I'm very excited for our science that we need so many mosaics. And how, well, I have more questions, but otherwise I can email you because there's a lot of challenges regarding the data, how you're going to handle it, and so on. But thank you very much. Let's thank Vincenzo.
Thanks a lot. It was a pleasure. And as I said, if you want to join the science team, I mean, some of you are already there, but everyone else is more than welcome.
Very cool. Bye-bye.
Bye. Have a good day. Ciao.
Ciao.
Ciao, ciao.